trebuchet is a type of catapult, which uses a swinging arm to launch a projectile. They are typically large constructions, up to 100 feet in height, and were used to knock down fortresses in medieval warfare. We decided to build a smaller one as a cool demonstration of physics.
The action of a trebuchet consists of a long arm, a short arm, and a counterweight, all connected by pivots. The projectile is attached to one end of the long arm, while the counterweight is raised. The long arm is held in place. When the long arm is released, gravity pulls the counterweight down, allowing the long arm to rotate. Then the projectile is fired. From this, you can probably work out that gravitational potential energy is stored in the arm when the counterweight is released by raising it to a height. When the long arm is set free, this potential energy is transferred to the projectile as kinetic energy. This is our trebuchet. After making a CAD model of it, we built it using the tools in Chris's garage, including a laser cutter, a drill press, and a machine saw. In theory, using the law of conservation of energy and inputting the dimensions of our trebuchet, we should be able to calculate the speed of the projectile when launched. We'll be using a counterweight of 11.34 kilograms, which will be raised to a height of 1.15 meters.
Plugging in the mass of the counterweight, 11.34 kilograms, as well as the height, 1.15 meters, through which the weight falls, we can find the potential energy that is being stored in the system and that is converted to kinetic energy. In this case, it is 127.8 joules. Now, because we know that kinetic energy is a result of all the potential energy, we'd say kinetic energy is equal to mv squared over 2, and the kinetic energy has to be equal to the potential energy at the start. Now, solving and plugging in the mass of 0.0585 kilograms for the tennis ball that's being shot, we find that the velocity is 66.1 meters per second in an ideal scenario where there's no friction and no energy loss.
Additionally, we can also calculate how far the projectile should be launched using the range equation, which is v0 squared sine 2 theta over g. Analyzing the footage, we see that the projectile is released at about 45 degrees. Plugging this into the range equation, we see that the projectile should go 437 meters.
However, these equations do not calculate the energy lost to friction or remaining energy that is left in the trebuchet arm and is not transferred to the projectile. To mitigate any loss in energy, we use a modern trebuchet design called the whipper trebuchet. It keeps the short arm of the trebuchet closer to the larger arm in the cocked position. The result is that when the arm is released, the counterweight comes to almost a complete stop. More kinetic energy is transferred to the projectile rather than the trebuchet arm, making the trebuchet more efficient.
So, how did this all work out in trial? Remember, if the trebuchet were 100% efficient, the tennis ball would be launched at a velocity of 66 meters per second and would travel a distance of 437 meters. Let's see what happens.
If we analyse the footage in slow motion, we should be able to determine the initial velocity of the ball. Let's have a look at the instant the ball is released from the sling. If we superimpose two adjacent frames, we can see that the ball travelled approximately 0 meters in 0.02 seconds. Therefore, we can estimate that the ball had an initial velocity of 0. This is significantly less than the ball's theoretical initial velocity of 66.1 meters per second. Additionally, the ball travelled a distance of approximately 0, which is also less than its projected range of 437 meters. let's figure out how efficient the trebuchet was. Remember, the trebuchet starts with 127.8 joules of potential energy in the cocked position. Using the formula for kinetic energy, 1/2 times mv squared, and plugging in the tennis ball's mass of 0.0585 kilograms and its initial velocity of 0, this yields a kinetic energy of 0. This means that our trebuchet had an energy transfer efficiency of 0. The loss of energy is because the trebuchet arm did not come to a complete stop after the projectile was released, and because of energy lost to friction or air resistance.
I hope you've enjoyed learning about our trebuchet and appreciate the role that physics plays in making this ball fly a couple hundred feet. This truly goes hard in the paint.